Thank you very much. Can you hear me? Thank you very much, Sebastián, for your very nice introduction. And also I want to, of course, to start by thanking the organizer for inviting me to come here. It's my first time in Valladolid. And as Sebastián has mentioned, I'm going to talk about something which is very classical in differential geometry of surfaces. In Riemannian three-manifolds, we are going to consider constant mean curvature surfaces. And just as a motivation for that problem or for that theory, here I have a first slide that says something about it. Surfaces of constant mean curvature, everything I'm going to say is going to be in a Riemannian three-manifold as an ambient space and just for surfaces. So everything is going to be extremely elementary. Can be viewed as critical points for the functional that you see there. You give me one real number h, and then I think of h as a mean curvature value, and then I consider the functional area minus twice h times volume, and then critical points for this functional for compactly supported variations, normal variations, are surfaces of constant mean curvature h. Okay? If you want to get rid of h and also the volume part of the functional, then you can just consider volume-preserving variations or infinitesimally preserving the volume. And for those variations, critical points of the area functional are CMC. CMC are constant mean curvature surfaces. Okay? But I don't prescribe H now. So in particular, if you fix a volume in a Riemannian three-manifold and you want to minimize among all domains that enclose this volume and you want to minimize area, and this is an isoparametric problem, then you will find minima for the second item. Okay? So in particular, there will be critical points and so CMC surfaces. The boundaries of this domain will be CMC. There are sciences which are interested in constant mean curvature surfaces, as here I have mentioned just physics and chemistry because of soap bubbles or foams or some interfaces that appear when you have two media at different pressures and they are meeting in some surface, say, and nature wants to minimize energy, which in this case means area, and then you find constant mean curvature surfaces. Of course, they appear within calculus of variations. Just the first and second item explain this. They also appear related to measure theory because the isoparametric problem. They are related to complex analysis, for instance, because there are many, many reasons. Right? One of them is because for a constant mean curvature surface in R3, the Gauss map is harmonic when viewed into the two-dimensional sphere. Okay? And you have a sort of Weierstrass representation. So if you give me a solution of the harmonic map equation into the two-sphere, then I can reconstruct a CMC surface in R3 with this Gauss map, okay? At least locally. And of course, and this will be important for my talk, there are many PDEs involved, I mean, in the sense of PDE methods, because as soon as you are talking about critical points of a functional, right, you go directly to the second derivative, no? To the second variation, and you are interested in if this is really a minimizer or not. Usually, there is not a critical point is not a minimizer. And then the second variation appears with a Schrödinger operator, which is that one, the Jacobi operator that you see in the slide. It's Laplacian in the diffuse metric plus a potential. The potential is the square length of the second fundamental form that I have called sigma for my surface, plus the Ricci tensor of the ambient space in the direction of the uninormal of the surface. Okay? And then, well, this is important because this has a discrete spectrum on compact surfaces. In particular, you're interested in eigenvalues and things like that. Oh, sorry. So this is going to be the main question that I'm going to work in the talk, which is to describe, to some extent, what are the CMC surfaces in a Riemannian three-manifold with the simplest topology. And I mean compact and among compact spheres, so very simple topology, okay? And of course, everybody knows that round spheres are the solutions in R3, okay? And, but the less symmetries you have in your ambient space, the more difficult the problems becomes. Okay? So now the next slide is in order to explain the main theorem of the paper, right? So I'm going to go directly to the homogeneous three-manifold. This means that I have a Riemannian three-manifold, and given any 2 points, I can find an isometry that carries one point to the other one. Okay? Which doesn't mean that the geometry of the space has to be the same in any direction. This is another thing. This is be isotropic. Okay? So I want to describe every aspect I can imagine of the moduli space of constant mean curvature surfaces in spheres, in such a Riemannian three-manifold, right? First item is about uniqueness. So if you give me one value of h, real number, and I think of spheres of constant mean curvature h, maybe there are no examples at all, but if they are, then you have just one up to moving the surface in space by congruencies, that is by isometries of the ambient space, okay? So that is about uniqueness. Existence. In order to answer for which values of h you have spheres of that value of the constant mean curvature, I have to go to the universal cover of M, the ambient space, that I call X, okay? Which is with a pull-back metric, again homogeneous, and of course simply connected. Then if this X is compact, then spheres of constant mean curvature in M exist for every value of the mean curvature. And if the X is non-compact, then they will exist if and only if the value of the mean curvature, well, there you see absolute value, but this is just a matter of orientation, so consider positive values, for instance, okay? So the value of the mean curvature is bigger than a geometric number, which is 1/2 of the Cheeger constant of the ambient manifold. The Cheeger constant is just, in this setting, is just the infimum of areas of boundaries of domains over the volume enclosed by the domain. Infimum among all possible domains, compact. Okay? And it turns out that this 1/2 of the Cheeger constant is equal to some other number that I will call the critical mean curvature of the ambient space, okay? That I will define later. And that a priori has nothing to do with the Cheeger constant, but it turns out to be the same. Okay? This is another paper that we proved some years ago. But I will say what is that for a moment. Let us just meet it as a notation. Okay? So now about symmetries. Spheres in R3 are round. Okay? So what can I say in a homogeneous three-manifold? Well, if you give me a H sphere, a sphere of constant mean curvature H, okay, then there exists a point that I'm going to call the center of symmetry of that. The sphere is not going to be, say, the boundary of a Riemannian ball. It's not true in general. It's true in R3, in S3, in H3, but not in other spaces. Okay? There exists one point in the ambient manifold so that any isometry of the ambient space that fixes that point will fix also the sphere. So the sphere inherits all symmetries of the stabilizer of that point, okay? In the space of isometries. About the moduli space, of course, if my spheres can be, I have one H sphere, so I fix H, then I can move the sphere all around the ambient space. So in order to talk about the modular space, I'm going to, say, normalize some way. So what I'm going to do is I fix a point in my homogeneous space, and I think of the class of all constant mean curvature spheres with that point as center of symmetry. Okay? And it turns out that this is a diffeomorphic, actually by a real analytic diffeomorphism, to the range of values of the mean curvature. Okay, which is the interval that I explained in item 2, where you see there again the critical mean value of the ambient space. Okay? Okay, about embeddedness. Are constant mean curvature spheres embedded in general? Well, in general, not. You have counterexamples. In certain examples of homogeneous three-manifolds, in Berger spheres, for instance, okay, you have values for the mean curvature for which the constant mean curvature sphere of that value, that is unique up to congruencies, is not embedded. So you cannot expect anything like that. Okay? But still, there is a weakening of embeddedness, which is Alexandrov embeddedness, which holds for every constant mean curvature sphere in any homogeneous free manifold. Being Alexandrov embedded means that is the boundary of an immersion. The surface is the boundary of an immersion of a mean convex free ball. Okay? Right. And the last property I want to mention is about the spectrum of the Jacobi operator that I mentioned before. Okay? Again, here you have what is the pointer? Well, I don't find the pointer. Here. This is again the Jacobi operator, and then there are two possibilities. Either you are in a very special case that I will say something later here in the B, or you are in the, say, completely generic case, which means, this case means you are not considering a minimal sphere in the product of S2, the sphere of dimension 2, of curvature kappa, constant, positive, with a real line. If you are not in that setting, then the constant mean curvature sphere, if it exists, that is governed by this item, it will have index 1, so 1 negative eigenvalue exactly, and nullity 3, which means that 0 will be an eigenvalue of the Jacobi operator with multiplicity 3. Okay? And in the other case, that is when you are considering minimal spheres in this ambient space with a product metric, then the sphere will be totally geodesic, stable, which means that no negative eigenvalues, and the nullity, so the multiplicity of 0 as an eigenvalue will be 1. Actually, I have written Soam, Rabasuam there because this line is not ours. I mean, this was known. Okay? Okay, something about the history of the problem. Well, the first three lines there are, I would say, classical. Okay? And then the fourth one will be less classical. So here I have written a result by Gelé in the 19th century. He proved that if you are in R3 and consider CMC, constant mean curvature spheres, but you impose star shapes with respect to some point, then the surface has to be round. So it has to be a round sphere. Hoff, 1 century more or less later, proved that you can drop that hypothesis of being star shapes. Okay? So if you have a constant mean curvature sphere in R3 or in S3 and H3, because the same argument works there, then it has to be the boundary of a geodesic ball, right? The main argument which is in the Hoff theorem is the creation of an object which is a quadratic differential that turns out to be holomorphic for constant mean curvature surfaces in those spaces. So in particular, if you are working with spheres, the quadratic differential has to vanish identically, the holomorphic quadratic differential. But vanishing of that means a 0 of the Hoff differential is an umbilic point of the surface. So this plus compactness of the surface means round sphere. Okay? Here I have mentioned another result by Alexandrov, which is in a completely different direction. He didn't assume sphere, but he assumed embedded. This has nothing to do with my talk, but I wanted to include it because it's very important for the theory, and I wanted to mention that. This is the origin of the moving plane method that is very useful in PDEs. Then, a little bit more recently, 2004, Average and Rosenberg extended Hoff's result to the, say, next level of homogeneous three manifolds. Here you have in this table the classification of homogeneous three manifolds. Those are classified in terms of the dimension of the isometric group. Okay? Here I'm considering only the case of simply connected homogeneous three manifolds because I'm dealing with spheres, so spheres can be lifted to the universal cover, so I can be in this case directly. If the dimension of the isometric group is 6, then you will be in a space form. And then is Hoff theorem. This is the ambient where Hoff theorem works. Next step is when the isometric group of the ambient space is 4-dimensional. These are the E kappa tau spaces. Kappa tau spaces are always submersion, Riemannian submersions over a surface of constant curvature kappa. This is one of the numbers, kappa and tau, that governs the geometry of this space. The second number, tau, is the bundle curvature. Tau equals 0 means that the space is a product with a Riemannian, the product metric. So for instance, here you have, in the case tau equals 0, you have either the product of the two-sphere, constant curvature kappa, with the real line, or of the hyperbolic plane of constant curvature, negative kappa, okay? With the real line. And in the case of tau different from 0, then you find Verger spheres, and this is something that I mentioned some minutes ago, okay, where certain constant mean curvature spheres are not embedded. Heisenberg group, the first one, Verger spheres, they admit Riemannian submersions over the sphere of the round sphere, two-dimensional. Heisenberg space, which is in this nil 3 fibers over R2, and the universal cover SL2R of the special linear group, or if you want, the universal cover of the group of orientation preserving isometries of the hyperbolic plane. Okay, but here in this last Lie group, you have a two-parametric family of metrics, left invariant metrics, that make this SL tilde to R an I kappa tau space. But the general left invariant metric for this Lie group is not of a dimension of the isometric group equal to 4. The generic one has dimension 3. Okay? And you have a 3-parameter family of those metrics. That is the reason why you see here repeatedly. It's the same ambient space. Actually, it's diffeomorphic to R3, but the group structure is the same, but the left invariant metric you put on this Lie group is different. Okay? And as I have said, all these are just submanifolds of the general class of Riemannian homogeneous three-manifolds, simply connected. All of them are Lie groups, in the case of an isometric group of dimension 3, and there you have, in the compact case, SU2, and in the non-compact case, that is diffeomorphic to R3, you have two possibilities, either a semi-direct product of R2 and R, given by in terms of a 2x2 real matrix, and here you have, I don't know if you can read it, but here you have the group structure if you give a 2x2 real matrix, A, okay? Or, as I said, SL tilde to R with the general metric, okay? So in summary, this is Hoff theorem, here Average-Rosenberg, and this part is open, was open, okay? Well, I had to mention a pretty recent result which was very influential for us. There's a couple of papers by Bill Mix and Benoit Daniel and Pablo Mira, where they solved the same problem for a very special case in here, inside here, okay? Because for certain A, well, here you have, here in the blackboard you can see choices of the matrix, and underneath you see what are the Riemannian three-manifolds that you construct, actually the Lie groups that you could construct with the semi-direct product structure associated to this matrix, okay? So what they did is they solved the problem of understanding constant mean curvature spheres for this matrix, which means in solve 3, with a very special left invariant metric, which is this one, okay? And they proved this result. So this is the framework, and what we're going to do is to try to explain a little bit how can you prove this theorem in the third column, because in the other two the theorem is known, okay? There you see MGL. MGL means metric Lie group. Metric Lie group is a three-dimensional Lie group endowed with a left invariant metric, which is the framework I'm going to work with. And I promised some minutes ago to define the critical mean curvature of the ambient space. Here you have the definition, okay? You consider in X, the universal cover, you consider the space, the class of all compact. Here I have written oriented or orientable, but it doesn't matter. You could consider non-orientable surfaces as well. Immersed surfaces in that X, but not necessarily of constant mean curvature. And then for any such sigma, you consider the mean curvature function. Since I don't know if sigma is orientable, I'm going to put an absolute value here, and then I don't have any problem. Sigma is compact, which means that I can compute the maximum of this continuous function on sigma. And then I'm going to take the infimum in the class of all possible sigmas. And this is the critical mean curvature of the ambient space. For instance, in R3 is 0, in Heisenberg space is 0, in H2 cross R is 1/2, in H3 is 1, okay? And it turns out that this number governs the existence of the constant mean curvature spheres. Okay? So what are the tools we're going to use in order to prove or give a sketch of the proof of the theorem? There are two. One is the Gauss map, okay, that I'm going to call the left invariant Gauss map. And second, it will be the notion of Killing graph. Okay? Well, think of the usual classical Gauss map in R3. But now I'm in a Lie group endowed with a left invariant metric. Then that means that left translations are isometries of my metric. So I consider an immersion F of a surface sigma into X. And I assume that it's two-sided. So it has a unit normal vector which takes values, this is n, into the unit tangent bundle of the ambient space. And I pick one point P in sigma, and I look at NP, which is a vector of length 1 in the tangent space of X at Fp. And then what I'm going to do is to left translate that vector to the origin. Okay? In R3, this is just translate. But in general, I will left translate, which is an isometry, and this way I create a map from sigma into the unit sphere in the Lie algebra. Okay? It turns out, and I'm going to call this the Gauss map, the left invariant Gauss map. It turns out that if I take conformal coordinates for my sigma, and I suppose that the immersion has constant mean curvature H, real number, then G solves a second order elliptic PDE. In the same way as constant mean curvature surfaces in R3 have Gauss maps which are harmonic. The equation is not a harmonic map equation. It's not of this kind, but it still is a second order elliptic, okay? Depending on H and also depending on the metric of the ambient space, also the left invariant metric. And conversely, the same thing that is as in R3. If you give me one solution of this PDE, at least locally, I can find an immersion of a surface of constant mean curvature H whose left invariant Gauss map is the solution of the PDE you gave me. Okay? Well, next step is what are the surfaces in my geometry that have constant Gauss maps, which is the counterpart of planes in R3. They are two-dimensional subgroups. The problem in my framework is that maybe you don't have any. For instance, U2 does not have any two-dimensional subgroup, or maybe you have such two-dimensional subgroups, but not for any value of the normal vector. Okay? And even maybe they are not the planes, the two-dimensional subgroups are not totally geodesic, and even they are not minimal. This can happen. Everything, you have examples in any of these. Very crucial in the proof, I will explain why. Fact, the left invariant Gauss map of a constant mean curvature sphere is a diffeomorphism. Okay, we will prove this. Second tool, Killing graph. Again, think of the left invariant metric. Because it's left invariant, if I take an element in the dual of the Lie algebra, so a right invariant vector field, okay, a right invariant vector field, then the one parameter group of diffeomorphisms is just made of left translations. So they are isometries. So the vector field is Killing, no matter what left invariant metric you pick. So these are algebraic Killing vector fields, okay? And a surface, an immersed surface, is called a Killing graph if, if there exists a non-trivial, non-zero, right invariant vector field so that sigma intersects, or the image of sigma of the immersion intersects transversally at most once every integral curve of V. At most once. If it intersects exactly every integral curve of V, then it's called an entire Killing graph. And it happens that, well, this will be the very end of the proof of the main theorem, okay? This fact, if you have a sequence of constant mean curvature spheres, all immersed in X, and the areas are going to infinity, now there is no reason to assume this, but you will see in some minutes why I will assume that. And the areas go to infinity, then first the ambient space is non-compact, and second, you can find a limit of such a sequence of spheres up to taking as a sequence and up to less translation, that converges to an entire Killing graph with respect to some right invariant vector field. Okay? One reason why this theorem is important is because in that, if I assume this sentence till here holds, then immediately I will know that the values of the mean curvatures for the spheres in the sequence have to converge to the critical mean curvature of the ambient space. And let me explain why. Okay? The reason why is a nice application of the mean curvature comparison principle together with some argument with foliations. So here you have the picture, I don't know if you see it, but here I have a sigma infinity, which is supposed to be one of these, say, lines. It's actually a surface. It's an entire Killing graph, okay? And because it's an entire Killing graph, if I move that surface by the elements of the one-parameter group of actually isometries associated to the right invariant vector field for which this sigma infinity is a graph, then I will create a foliation of the ambient space by surfaces which are congruent copies of the sigma infinity, in particular with the same value of the mean curvature. Okay? All of them. This is a foliation of the whole space. Now, just by the very definition, the critical mean curvature of the ambient space has to be less or equal to the critical mean curvature, to the mean curvature of any of the spheres, because the sphere is compact. So you have this for free. By taking limits, then the critical mean curvature of the ambient space will be less or equal to the mean curvature of the entire graph. Because this is the limit of, sigma infinity is the limit of Sn. Okay? Forget about this part for the moment. Now, I want to show that this inequality actually becomes equality. So suppose not. Suppose this is a strict inequality. Since this is an infimum, by definition of the critical mean curvature of the ambient space, that means that you can find this guy here. You can find a compact immersed surface so that the maximum of the absolute value of the mean curvature function, not necessarily constant function, will be arbitrarily close to this infimum. In particular, will be less than this number. Now you have this new surface, this one, which is compact in space, okay? And just because you have a foliation, you can think of a copy of sigma infinity in that a leaf of the foliation, which is this joint from that, because that is compact. And now you start approaching. And look at the first time in the foliation that the leaf intersects that compact surface. And there, at that point, you compare mean curvatures. And just in the picture you see, the mean curvature of this leaf has to be less or equal to the mean curvature of that at this point, okay? Which is the opposite as what we had. So that's a contradiction, which means that you have arrived to the desired value, critical mean curvature of the ambient space, okay? So this will be the very end of the argument. So now I'm going to devote my half an hour, more or less, of my talk, the second part of my talk, to giving a sketch, okay, of the proof, of the main thing. Right, so I start with a simply connected, I go first to the universal cover. I said I can go, right, by lifting spheres. I go to the universal cover, I put there the pullback metric, so it's simply connected homogeneous. And then it will be either, this is an old theorem, either isometric to the product of S2, certain curvature, with the real line, but in this case, this is an Ikapatau space, so the theorem is known. I'm not interested in that case, okay? Or it will be a metric Lie group. So from now on, I'm going to work always in a Lie group of dimension 3, right, with a left invariant metric. So now, I know that left translations are isometries because the metric is left invariant. That means that I can produce for free 3 linearly independent functions in the kernel of the Jacobi operator of any sphere of constant mean curvature, which are given by taking the normal part of the variation given by left translations. If you take a killing, here I have said killing, but think of right invariant, that implies killing. If you have a right invariant vector field on X, and you have a CMC surface with normal, uninormal vector n, then the inner product of the vector f with n defines an element in the kernel of the Jacobi operator, which is called a Jacobi function. I'm going to use this a couple of times, okay? So that means that I can produce 3 linearly independent, 3 because you have this dimension in the Lie algebra, linearly independent Jacobi functions on your sphere, okay? Which means that the multiplicity of the 0 as an eigenvalue of the Jacobi operator is at least 3. I don't know if it is 3 or more, but at least 3. But the first eigenvalue of the Schrödinger operator on a compact surface is simple. So 0 cannot be the first eigenvalue. You have to have at least 1 negative eigenvalue, which means that the index, the number of negative eigenvalues, is at least 1. So that's a motivation to study, instead of the general problem of CMC spheres, study index 1 CMC spheres. Maybe, and this is what happens in the end, every sphere has index C, every CMC sphere, okay? There is no reason to assume, to suppose this is going to be the case, but in the end, this is what happens. Okay, so now I consider the class M1 of CMC spheres of index 1, modulo left translations, okay, in my ambient space X, metric Lie group. First, that class is non-empty. Why is non-empty? Because if you try to solve the isoparametric problem for very small values of the volume. You can do it for any value of the volume because you are in a homogeneous three-manifold. But do it for very small values of the volume. Then a blow-up argument says that if you blow up such a solution of the isoparametric problem, you will find a sphere which is nearly round. Very tiny sphere. But that sphere, for free, will have index 1. Why? Because it's a solution of the isoparametric problem. That implies that. Okay? So in this class, you have elements to start working. So first, I said that the nullity is at least 3. And now I say it has to be 3 for any element in any index 1 sphere. Why? Because Cheng's theorem says that you cannot have more than multiplicity 3 if you have just 1 negative eigenvalue. And since I'm considering index 1 spheres, I am in this setting. Okay? Good. Once I know that the nullity is 3, I know not only I know the nullity is 3, I control exactly the kernel of the Jacobi operator. I know what are the functions in the kernel. Are those functions in the corner of the blackboard? Okay? Which means that I can do a standard implicit function theorem argument to the mean curvature operator, and then prove that around any element in M1, you can locally parameterize M1 by a real analytic parametrization. So it's a one-dimensional interval, say. Locally around, just locally. Now, take an index 1 sphere. Then I claim the Gauss map, the left invariant Gauss map is a diffie. This is something I said before. But I said this for any CMC, not for index 1. Now I'm going to prove it for index 1. Okay? At the end of the day, every CMC will have index 1. Okay? So why? Because if not, since I'm working with spheres, sigma is a sphere, then G will fail to be a diffeo means that will fails to be a local diffeo, okay? Which means that you find a point where the differential of G has kernel, non-trivial kernel. So that creates a point P and also a right invariant vector field just by extending the vector at field that lies in the kernel, so that the corresponding Jacobi function NF, the one that you see in the corner of the blackboard, vanishes with second order at P, vanishes with second order. This property of vanishing with second order means that if you remove from sigma the zero set of the function, you have at least 3 nodal domains. But this is again forbidden for an index 1 sphere by Chen. Okay? Which means that, G is a diffeo for index 1 spheres. Now, you fix one element in M1, and let us call H the value of the mean curvature for that element. Okay? And I claim that that is the unique sphere, no matter if index 1 or not index 1, for that special value of H, of the mean curvature. So I repeat. If I take one index 1 sphere, that is, for that value of the constant mean curvature, is the only element in the total class of CMC surfaces, CMC spheres, with that value of the mean curvature. Why? This is where we use the ideas in Benoit Daniel and Pablo Mira and also Bill Mix. Because with the fact that the Gauss map is a diffeo, you can use the inverse map of this left invariant Gauss map. You can use G-1 to produce an object which is a non-holomorphic but smooth quadratic differential. Okay? It's not holomorphic, but still it has isolated zeros of negative index. So if you are working on a sphere, then Poincaré-Hopf theorem tells you that that object will vanish identically. Again. And the vanishing of this object is exactly the same as saying that the surface where you have the object defined is a translation, left translation of sigma, which means that sigma is the only CMC sphere with that value of H. Okay? Now I fix a value of the mean curvature, a real number, H hat, large enough so that with everything I have proven so far, so that the moduli space of H spheres with values of the mean curvature, at least this H hat, is diffeomorphic, real analytic diffeomorphic, to an interval of this form. Okay? And what I'm going to do is to start deforming the value of the mean curvature by using the implicit function theorem, but decreasing the value of the mean curvature. Okay? So I start deforming. So that means that I have started here. From this point on, M1 is just an interval. Okay? And I start deforming by using the implicit function theorem till I cannot deform anymore. I would like to explain, say, the following properties. First is that as soon as I deform analytically, I will never leave M1. Not only that, I will know that no other sphere will be in this part of the picture. So that's the only thing you see where the range of the red curve occurs. Okay? But maybe you find an obstacle in order to go beyond that point in terms of keep the deformation, continue the deformation, right? And the obstacle, I want to show that the obstacle happens for a value of the mean curvature which is exactly the critical mean curvature of the ambient space. Because arriving to that point will mean that I have finished the proof. That means that for every value of H in the correct range, you have exactly one sphere, no other constant mean curvature spheres. It doesn't, and in particular, every sphere will have index 1, etc. So that is the end of the proof. Once I know that if I do this, say, prolongation argument, the obstacle doesn't happen before arriving to this value if you decrease the value of the mean curvature. Okay? So, so take a maximal, say, component or range of the mean curvature so that you can do this, a maximal range, okay? And suppose that it happens in an interval of this form, h naught of x, okay? And just by elementary elliptic theory, you know that in order not to be able to extend this argument is because either you lose curvature estimates along this parametrization of the modular space, or you have areas going to infinity. Okay? These are the only two possibilities that can go wrong. If both of them go okay, then you can keep going. You can extend this. Well, curvature bounds, or bounds for the second fundamental form, are for free. I mean, here you have more or less an argument that explains why. If you fix a value here, for instance, okay, and you consider all constant mean curvature surfaces below that level, or spheres below that level, okay, you have for free uniform bounds for the second fundamental form of such surfaces. Why is that? Because of a blow-up argument. Here I have written some argument, but yesterday I thought that it was, well, no, it's more natural to say the following thing. Okay, here I explained some minutes ago that you can think of this as isoparametric spheres, where the value of h is extremely large and the sphere is very tiny, very, very, very small. The area is very small. Okay? But for those isoparametric spheres, it's easy to prove by a blow-up argument that because they are nearly round, the degree of the left invariant gas map is +1. The degree is 1. Okay? But if you lose bounds of the uniform bounds of the second fundamental form, then you can do a blow-up, a rescaling, okay, when you go to this accident. Okay? And because the mean value, the mean curvature value is decreasing, okay, when you do the blow-up argument, you find a minimal surface in R3, minimal. But the Gauss map of a minimal surface in R3 has non-positive degree. So you cannot pass from degree 1 to non-positive degree. This is impossible, okay, along this deformation. This is the reason why. So curvature bounds are guaranteed, okay? So the only thing that can fail is to have area bounds. And then you see if I have an obstacle to go beyond that deformation argument is because I have a sequence of spheres of index 1, now of index 1 because I'm coming from the red curve, whose areas go to infinity. And so that the values Hn of the mean curvature of these spheres descend to some limit value that I call h naught of x. And I want to show that h naught of x equals critical mean curvature of the ambient space. And then here I have rewritten the theorem 2 that I showed you before and explained more or less the proof. The only change is that now I have included M1 because I can reduce myself to M1. Okay, and 10 minutes, good. Okay, so the point is how to prove this theorem for a sequence of, of index 1 constant mean curvature spheres with areas going to infinity, okay? Well, I will say something about this, not too much, but something. Of course, I want to study limits, non-compact limits of spheres because the area is going to infinity, okay? So I'm going to consider the class of possible limits that I call lim M1 of what? Here, look at the picture and it's much easier to understand. You have a sequence of spheres of constant mean curvature. These are those, okay? Actually, the spheres are floating around because you are considering sphere up to left translations, okay? So the first thing I'm going to do is I'm going to consider limits of certain subdomains that I call omega here, once I have picked a point Pn in omega n and left translated my immersion, so I have normalized all immersion by left translations so that they map the point Pn to the origin, to the identity element of the ambient space, of the Lie group. Okay? So this is my situation. I have a sequence of constant mean curvature spheres, which are these dotted curves. Actually, they are spheres. Areas are going to infinity. Okay? And because I explained they have curvature bounds, I can take limits. And I find something which is non-compact, some sphere which is non-compact, some immersion is complete non-compact with the value of the mean curvature equal to the limit value, which I called h node of x. Okay? But if you think a little bit on the Gauss map, about the Gauss map of the sequence, it is a diffeo for any element in the sequence. Okay? So you can think of this first limit as a kind of, I don't know, a paraboloid or something like that. The area, the image of the Gauss map of this first limit, of this blue limit, is, I can think of, say, a hemisphere or something like that. I mean, it's an open domain in the sphere. Still, the Gauss map is injective, because if it is not injective on its image for the limit, it would fail to be one-to-one for the elements in the sequence. Okay? But I don't want this. I want something else. I want to find a limit whose Gauss map, the image of the Gauss map, is just a curve. And again, the image of the Gauss map of the blue guy is, say, an hemisphere. Is an example. Right? It's not necessarily an hemisphere, but how am I going to do this? By performing what I call, this is a first order limit, then I'm going to define a second order limit. What is a second order limit? Well, in this picture is consider a sequence of points, but now on the blue guy, diverging, and by a left translation, put those points at the origin again and take limits. So, in a sense, think of a kind of a paraboloid which is asymptotic to a cylinder. The paraboloid is the blue surface. And what I'm going to do is to take limits so that I lose the paraboloid, okay? And what I find in the limit is the cylinder. The cylinder has a Gauss map which is a curve. And that's very important for the argument, okay? So this is the class of second order limits. It's more or less copied the definition of first order limit, but once you have picked a first order limit, you consider now limits of left translations of the first order limit by a sequence which is diverging in the image. Okay? What happens is that that limit class is non-empty, and also this limit class is non-empty. And this comes from curvature bounds. Okay? Now, every first order limit has index at most 1. This is very easy because it's a limit of spheres that have index 1. And you cannot increase the index along a limit. But the crucial thing is that for a second order limit, the second order limit is stable. That is extremely important, stable. Why stable? Because otherwise you contradict that the first order limit has finite index. In fact, index 1. Okay? Once you know this, okay, using stability, you show that the rank of the differential of the Gauss map for the second order limit is constant. It could be 0, 1, or 2, because it's a surface. Constant on the surface. 0 means that the Gauss map is constant along the surface, which gives you that the surface is a two-dimensional subgroup. 1 for the rank means this, that there exists a right invariant vector field which is everywhere tangent to the immersion of the second order limit. This, geometrically speaking, means that your second order limit is constructed in the following way. It's like a cylinder. You have a generating curve, alpha, living in X, and on top of each point of alpha, of the image of alpha, you put an integral curve of a fixed right-invariant vector field. So your second order limit is ruled. It's a ruled surface. And the ruling is just a collection of integral curves of a given right-invariant vector field. Okay? This condition, this property, gives you a lot of information about the topology of your second order limits. Okay? And I should, okay, so in order to finish, I would say only that once you have arrived to this point, what you do essentially is you study cases depending on what? Depending on the topology of your second order limit, and also depending on the character of the right-invariant vector field. Because these are completely classical, no? You give me one Lie group of dimension 3, and then I know what is the Lie algebra, then I know what are the right-invariant vector fields, and I know the properties of their integral curves. So the problem reduces to study a problem on, say, ruled surfaces, those kind of surfaces. And in the end, you can prove the theorem this way. So there is a limit of your sequence of index 1 surfaces, spheres, which is an entire Killing graph with respect to some right-invariant vector field. Okay? So that's all I wanted to say. So thank you for your attention.